Hello, I'm Taylor Witten, and I'm going to be covering linear probabilistic modeling. The linear probabilistic model is a model of the relationship between a dependent and one or more independent variables. It effectively constructs a linear function that can be used to predict future outcomes. It's very similar to the algebra equation y equals mx plus b. However, the difference being that this model takes into account error, allowing for points to fall above or below the line as they will in the real world. The linear model can be used anywhere that a dependent variable and one or more independent variables need to be related in a somewhat linear fashion. This will vary based on what the data set is. In this example, the x-axis represents the number of LEDs that a firm produces. The y-axis represents the number of defective LEDs in each batch. So for 100 LEDs, 4 are defective, 200, 5 are defective, 300, there will be 9 defective, and so on. Looking at this data, it appears that there's a relatively linear relationship between the number of LEDs that are produced and the number of defective LEDs. With this information, it can be assumed that one can create a linear probabilistic model of this data set. When performing linear probabilistic modeling, one uses the linear regression model. The equation used in this model is y equals b naught plus b1x plus epsilon, where epsilon is a normally distributed random variable. The mean of epsilon is equal to 0, and the variance of epsilon is equal to the variance of the population. Y equals b naught plus b1x is the true regression line, which basically estimates where each point should lie should there be no error. Each point will lie above or below this regression line based on how much error is associated with the point. Beta naught and beta 1 are not just arbitrary values, they're calculated from the data set. Beta 1 is calculated using the top equation, which gives the least squares estimate of the slope of the true regression line b1. This b1 value can be either positive or negative, with a positive value representing a positive relation and a negative value representing a negative relation. Beta naught is calculated from the bottom equation, which gives the estimate of the y-intercept of the true regression line b naught. The normal distribution determines how far one can expect each point to lie above or below the regression line. A high variance value will cause one to expect the points to be quite far apart from the regression line, while a low variance value causes the points to be tightly packed around the regression line. Thanks for watching, and I hope this helped with your understanding of linear probabilistic modeling.